Welcome to the third installment of my implementation of the Ray Tracer challenge by James Buck, where I'm learning Rust while I'm implementing all of this Ray Tracer stuff from
Hello, just a short intermission from a little bit wiser and older Jacob, which by now has done some of those recording sessions and some more streams, and has realized he forgot to tell you that there are information in the description below regarding the GitHub repository where you can get all the code we are writing here to follow essentially along. Furthermore, please bear with me while I'm still learning on how to present all the different things I'm doing currently during the recordings. I get better from recording to recording, from session to session, so please be a little bit patient. And now, back to the program. Have fun.
And I have some wine here, and yeah, so cheers. I've actually made the glass a little bit fuller than I normally would, but so I can drink while I'm doing this session. So where have we stopped? Let's take a look. Let's see. We have just rightly so implemented the calculation of the magnitude of a vector, so the length essentially, and the normalization of a vector, so making it a vector of the size 1. So let's run our tests again. Okay, we have still 23 tests and they are all passing. That's a nice thing. By the way, in the meantime, I've actually initialized the Git repository and made the first commit. You will find all the information in the description just below the video on how to access this. And I've decided to now more than before commit the different single steps to the repository in order to have a nice development history there and to be always on par with the videos I'm publishing, so that you can follow along and have the code ready to be used. So we are still in chapter 1, but we are nearing the end of chapter 1. And what was the last thing we had to do before I decided to take a break? It was the implementation of the dot product. The dot product of a vector, no. The dot product of a vector is actually a scalar result. If two vectors are multiplied, or the dot product of two vectors is created, then a scalar value will be the result. The dot product gives us certain information about things like, for example, the angle between two vectors, or how much they differ. We can easily determine, for example, if one vector is on the other side of a vector and stuff like that. So we will go now there and implement this. And as always, we are doing it by implementing the test first. So let's go ahead and declare a new test here and what should we call it? We should maybe call it, again, as we did before, the dot product of two tuples is the name of this test. So yeah, why not? The dot product of two tuples. Sounds good to me. So what do we actually have here? We have two vectors here, but that's the strange thing. Actually, this should be called of two vectors. Essentially, we are calculating, of course, the dot product of two tuples, but the test actually is only testing vectors. So I will change this, even though in the book it is called differently. This wine is really nice, by the way. So we have the vectors. Let A tuple vector 1.0, 2.0, 3.0, and let B tuple vector 2.0, 3.0, 4.0. Okay, yeah. Could have guessed that. So yeah. And then we want to calculate the dot product of those two. And now let expected result be 20.0 because that is the expected dot product, and let the actual result be, I guess we are implementing it like a dot b, I would assume. Or are we actually in mathematics, in mathematical formulas, the dot product is often marked as simply the dot, like a multiplication. Maybe we want to override the multiplication operation of two tuples if they are two vectors and not a vector and a scalar. I'm not 100% sure if we want to do it this explicitly or not. So otherwise we could write a times b, but it's not strictly speaking a times b, so no. I think we will explicitly call this dot function. Yeah, I actually like this better, I guess. So we can always change it if we like. So this would be assert equals actual result, expected result. By the way, I got asked why I'm always doing this, setting the values here and then essentially only calling or asserting them here, because this is mostly always the same, as you can see here, what I'm writing there. I actually like this better. Essentially what I was asked is why don't I write this here like assert equality between a dot b and 20. And I can't really tell you why I do it this way, but I actually simply like it better. I think this is easier to read, or this is easier to read for me if I'm glancing over the tests, as I'm always doing it in the same way. I can always easily see the expected and the actual, and the assertion is just below it. It's more or less just the call to do it, to do the assertion, but it's not the value itself. And there is the added bonus. If we have something, where did we have something like that, where we actually need to have different assertions on a result, we can easily do this without having to calculate things all over again. So yeah, I guess that's why I do it. I simply like it better. So yeah. Cargo test. Okay. Actual result. Yeah. We just found out that the dot product method, or function better thereof, is not yet implemented. And that's correct. We did not implement that. So let's implement it. It's a public function called dot, and it will take self, of course, and it will take, come on there, other, which is a tuple. And it will return a new, no, it will not return a new tuple, it will return a 64-bit floating point number. So expected parameter name found %. Yeah, maybe I should have written an ampersand there. So tuple found reference node, expected struct tuple found, wait, what? Mismatched type, expected struct tuple, found reference node, expected struct tuple, found reference. That's kind of, is it this way? Okay, it seems that this is the short form, of course, but it's other, and yeah, okay, it's the parameter other, and I'm expecting a reference to a tuple. Yeah, okay. So what we are going to do here is this return again. Maybe we will, just for better readability, I'm doing this. Maybe I have to delete the parenthesis later on again. So this is self.x multiplied with other.x plus self.y plus other.y, multiplied with other.y plus self.z multiplied with other.z plus self.w multiplied with other.w. So unnecessary parentheses. Yeah, I guessed that. Okay, then let's just do it like this. Can we actually? I would love to have it in a multi-line like this, but I'm not sure that the formatter will most likely, yeah, put it all into one row again. So yeah, that's actually the dot product. The dot product is multiplying up each of the different components and adding them together. That's kind of how the dot product works per definition. So we've now implemented that. So let's check what our tests say. It can't be compiled because actually it's expecting a tuple reference. As far as I know, I can always only borrow the struct to one target inside a function. So maybe it's not that good of an idea to have something like this here, which would work in this case, of course. But can I just let me check something with regards to Rust, which I don't know yet. Not used. Let's just say b dot b. Can I do this, or is it just then not compiling? So okay, this is working actually. So maybe it's not that bad to borrow this value here, but wait a second, didn't we have something like this before? No, we did not. I guess this is actually the right way to do it in Rust. I hope. So yeah. So yeah, let's drink to that. Cheers. So okay, now we have the dot product, and essentially we have one test for it. I guess that's enough. Yeah, there is nothing more to test. So the next thing we want to implement is the cross product. The cross product is actually the result of two vectors. So the cross product is vector 1 cross vector 2, and the result essentially is another vector. And the cross product of two vectors is always a vector which is 90 degrees in three-dimensional space to both of the other vectors. And this is quite useful actually, and we will later on, of course, use it for a lot of different stuff. So let's write another test here. So fn, and it's called, how is it called here? The cross product of two vectors. Oh, okay. Cross the cross product of two vectors. And it's essentially, let's take a look at what is, it's essentially the same, or mostly the same code again. It's those two vectors actually. And so expected result let's call this of two vectors 1, and let's do a second one and let's call it of two vectors 2, because the cross product is actually it's different according to where the where each component is represented. So if we do A cross B, it will be something different than B cross A, as it is essentially it's a vector which is a 90 degrees to the other two vectors, but it will be in the other direction. So in this example, one will go there and one will go there. So yeah, let's implement those, and it's using here the same two things, and of course the expected result now is a vector as well. So we have this vector here, and it should be -1, 2, -1. No, this is actually the result for A cross B. The other one should be exactly into the other direction. That means like this. Yeah. So, of course, if we compile this, method not found in tuple. Of course it is not. We haven't implemented it yet. So let's implement it. Let's implement a pub fn cross self other tuple. We are again. Are we really implementing this on a tuple? I'm not really sure that we do. No, we do not. We are explicitly implementing this only on vectors, so we have to take care of this, because, and this is important, a cross product in 4 dimensions is a lot more complicated than the one in 3 dimensions. There is a generic formula for creating and calculating a cross product, but it will be immensely more complicated with each dimension added to this cross product. So we don't actually want to do that. So we definitely want to only calculate this on vectors, and we have to check how and in which way we can do this in Rust, because we only have this function is vector, or we can check on the 4th dimensional parameter we have in a vector, which is w in our case, to ensure it is a vector and not a point, for example. But I'm not sure we can actually tell this system that we want want something more specific here. So nevertheless, we can do it as we are doing it during runtime. We can do it in another way. We can simply say if self dot is vector, if not, or other is vector fail. I guess this is a macro. It's not. how is this fail function gonna work? Rust fail function? So, yeah, no, I want to unrecoverable errors with panic. I see. Panic, crash and burn. I see. Yeah, I want panic, not fail. Panic. So panic would be cross product can only be calculated for 2 vectors. Dot. So if this is the case, we want to do this, and otherwise we are calculating the dot the cross product, which actually is something I need to more or less copy from this implementation because I can never really remember. So what we do, what do we want here? We want self.y multiplied with other.z minus self.z multiplied with other.y. But this is the first component, so it's a tuple vector. Yeah, so this is the first component, and the second component will be self.z multiplied with other.x minus self.x minus multiplied with other.z. And the second and the third and last component is self.x multiplied with other.y minus self.y multiplied with other.x. So, and essentially you can see why this is why this is called cross product, because we are more or less doing it multiplying the values crossing each other. So yeah, so this is the second one is here, the yeah, it's kind of always crossing. So why is there still an error? Mismatched types, expected struct tuple found. So it is unnecessary parentheses around if. Let's remove them if it doesn't want them. So why is this not? Oh, because I have a semicolon there, and return values don't have a semicolon. That's still kind of strange syntax to me, but okay. We have this cross product, which maybe we can calculate now. Yeah, we now can calculate a cross product. So I guess we are finished with this implementation. So let's just check. Okay, let's commit this. Git add source main rs git ci -m finished library or finished tuple struct implementation from chapter 1, and let's push this. So yeah, that's nice. So yeah, clear. There we go. We are done with the implementation of this tuple, and before we are going along with the next chapter, we definitely need to take a look at how to structure code with Rust, because I now want to extract all this tuple implementation and test stuff we have here into a different file somehow. We need to take a look at how this works. But in the meantime, I guess it's time for us to finish up this chapter by implementing the first test or application, which is putting everything together that we have just wrote. So maybe we can move this up here. This seems to work nicely. So yeah, what we are going to implement here now is from this book, and it's simply putting everything together, which is essentially, we can't ray trace anything yet because we don't have that, haven't written that much code, but actually the program we are now going to write, which is using all this stuff, is according to the book doing the following things. It is a virtual projectile firing system. So it will fire a virtual projectile and will then calculate how far those projectiles go. And this is essentially something where we need all this vector and tuple stuff we have just written for. So let's do this. It says here that we need some stuff for that, actually. There will be a function called tick in the end, which will, I guess, somehow calculate each step of the flying sequence of this projectile until, I guess, it's reaching the end of its life cycle. So this is the function, and it gets an environment, and it gets, what does it get? The projectile. So why not call this environment world? That's my understanding of it now. I've just skipped over it, but let's take a look. I guess that is right, because there's something like gravity, for example, within the world. And the projectile will be a projectile. Projectile. And does it return something? Yes, it returns the newly an updated projectile. So yeah, I guess we have this then. But this implies that we have a struct called world here, which holds certain information. I'm not sure which yet. And we have a struct called projectile here, which holds certain information as well. So yeah, let's go with that. What does the world actually have in terms of information? A projectile has a position and a velocity. So let's start here, if this is the first thing that our projectile is written out here. A projectile has a position and a velocity. And the position is, of course, a point, and the velocity is a vector. So yeah, we can actually quite nicely do this. So we have a position that's a tuple, and we have a velocity, which is a tuple as well. So what does world has? World has an environment has gravity, which is a vector, and wind, which is a vector as well. So we have gravity, which is a tuple, and we have wind, which is a tuple. And we have it in those, in those structs. And I guess I want this tick function inside the projectile, because we are actually transforming and moving this projectile forward. So let's do this impl projectile, and it will have, or maybe not. I guess, oops, what did I do there? Let's get this function back here. So mismatch types expected. Yeah, it is not returned yet, but it should work nevertheless. So we have a projectile, and this one has a public function tick, which then takes essentially an environment in which it should tick forward. Maybe the projectile should know its environment or something like that, but that's out of the scope for this one, I guess. So what should this function do? According to this implementation here, or to this book, yeah, it should update its position based on the velocity of the projectile. That makes absolute sense. And then it should adjust the velocity of the new projectile according to the world's gravity and wind. That makes sense as well. So let's do this. Let's do essentially we are missing a self here. So let's do a self dot what is it? No, self position equals essentially self position plus and no, self velocity. No, wait. Are we are not, I don't want to modify the, we are not implementing this inside the projectile. That's not, maybe it is a good idea, maybe it is not, but actually I want it like this, I guess. Let me just think a second here. Projectile, and we want to return a new projectile, and this is something we are actually implementing on. Let's do like this. So we have something like projectile new. That is something we still need to implement, and we want to give it a new position, which is based on the old projectile's position plus the projectile's velocity, which is essentially now adding to adding the velocity vector to a point. That makes absolute sense. And for the new velocity, we want, there's a typo in there, projectile. And for the new velocity, we want to update it by using the current velocity of the projectile, and we want to add the environment's gravity and the environment's wind vector. Wind vector, yes, that should do the trick. And this is what we actually return. So we now need, of course, impl projectile, and there will be a pubfn new, which will take a position, which is a tuple, and it will take a velocity, which is a tuple, and it will return a self, and it will do so by simply instantiating this thing with a position and the velocity. There we go. And we actually, I guess, want the same thing for the world, but with gravity and wind, I guess. And this would be gravity and wind. And because the book is calling it this way, I will, yeah, I know, the shortcut doesn't work. I haven't fixed that yet. So I guess I'm calling this environment as well, just for the sake of it. So now it's called environment. Yeah, we are not using this yet. I'm aware of that. Private type environment and public interface can't leak private. Does this really need to be public? Associated function is never used. New. Yeah, but isn't this function is never used? Ah, okay, it's bubbling up there, I guess. So yeah, let's kind of implement our main function here now then. So I guess we are let environment equals environment new, and let's tuple vector. What are they doing here? We can play around with it a little, but let's start with something here. It's minus 0.1, and this is 0. This would be our gravity, and for now let's simply assume the wind vector is 0. There is no wind. And now we initialize our projectile. This would be projectile new, and it would be a tuple, which is, no, the position is a point, which would actually be, where could we position it? We could position it at the 0 point in x direction, then we could put it, I guess, somewhere in the y direction, so somewhere in the air, I guess. And maybe in z direction 0 as well. And then we have a velocity vector which might be moving somewhere, like, let's move this one in x direction with a speed of 0.02, 0 here and 0 here. So this could be done like this. And there we have just a mismatched type thingy. Yeah, it's unused, I know. So what I'm going to do now is I'm ticking it forward, so I'm moving it through time until it has been fallen on the ground. So fallen on the ground would mean that it actually touched the y-plane. So I guess if y is less than 0, less or equal to 0. Now we want to do something like while projectile dot position dot y is bigger than 0. So while we are still in the air, we are doing the following. We are calling tick with our environment and our projectile, and we are getting back another projectile which we are storing here. Cannot assign twice to immutable variable projectile. Ooh. So let's create let mute current equals to projectile. And then maybe do it like this. Use of moved value projectile, value used here after move. So that's wrong. Actually, the system you moved here in previous iteration of loop. So what? use of moved value. I see, because our tick should actually only use references to this variables, because after they have left this processing cycle, they could actually be reused if we wanted that. So let's just push in the references there and we should be good. Okay, I see. So now how was this all this printing going? The hello world I just deleted. Git diff. Let me see. Print line. That was print line. I remember. So easy if you know how to do it. Print line. It's a macro. So let's have a mute I 64. We will hopefully never overflow this. It's like iteration. It's I32 should be completely enough. So this is iteration 0. So iteration 0, that's something we want to print. So that's the iteration and then a dot. And then we will print our, how was it done? Like this? I'm not sure if this is the right syntax. So I want actually to print iteration plus plus. And then I want to print current. And that is something I will not be able to do actually, I guess, because the system does not know how to print this. So I need to have something like, how was it done? Derive, and then I did it here, debug copy clone. I guess debug should do it, maybe. Oh, it's at the wrong position. It should be here. So, expected expression found plus. Maybe this is not invalid format string. Yeah, I guess I need to I want colon question mark here. So. Yeah, it does not need to be mutable now, because now it's like iteration plus equals 1. Now it needs to be like this. So yeah, and I guess we will simply do this one last time and we'll say finished, like this. So let's check if we can actually, I guess it was like this. Okay, it seems to work actually. So we have 5 steps. We are moving the position slightly by x because it is essentially traveling in this direction, and we are actually moving down here. That's the gravity taking care of accelerating us down. It's essentially accelerating as well, so we can see that here, until we then are below the 0 mark. So yeah, that really seems to work. And we have velocity, which is essentially the same in the x direction, because nothing is interfering with the x dimension of this movement. Yeah, I like this. But the y direction is accelerating downwards, which is done by gravity. Yeah, in z direction, no movement at all. that seems to work quite nicely, actually. Yeah, I think we have just finished chapter 1, and I like that. So maybe you should at least print out with what kind of environment we are working here. So let's print line. Yeah, I guess let's just print that out. Come on, environment. This will not work because I have to derive the debug type here. And this should be a small d. So yeah, there's our environment, there's our gravity, and there's our wind, which is actually 0. So maybe we could add a slight wind, which is blowing from the other side of X. Then this thing is moving. Really, really slight wind here. And let's take a look at what happens then. And now actually we should be moving into this direction as well. Yeah, now X has some wind resistance here, or has some wind applied against it, so it is moving in X direction as well. But essentially the velocity, yeah, the velocity changes ever so slightly into the X direction. Yeah. Yeah, that sounds actually quite right to me, so that's nice. Yeah, I like that. It's working out like it should. And essentially, this is the end of chapter 1. Chapter 2 will actually then be, I guess, from the title, the start of implementing some canvas to draw on. So I guess some data structures to store and hold RGB values or of some kind, and to define some pixels in it, and to then somehow do all this magic we want to do with a ray tracer later on. So I guess this sums up the chapter 1. So let me commit this. Git add source main git ci implemented example from chapter 1. And let's push this. Yeah. This has taken me a lot longer than I thought it would, but yeah, I'm a little bit tipsy. The wine is mostly empty. Now it is empty, but it was delicious. And yeah. I wish you a nice evening, or whenever you are seeing this, a nice day, or something like this. I hope you will be again there with me to take a look at the next chapter of this this book, which I until now really much enjoy implementing and taking a look at Rust in the meantime, and learning Rust a little bit. Yeah, so until then, I wish you the very best, and see you in the next section, hopefully. Bye!